let's reset and start all over. Hello. So I just realized I forgot to hit the go live button about an hour ago. Rookie mistake, and I'm gonna blame the lack of sleep over the last little while. I knew something was wrong subconsciously, but sometimes you don't listen to that subconscious voice. But that actually lets me kind of recap everything I've covered so far. And honestly, so far the stream has been very cut up anyway, because I've been totally forgetting. I've had to interrupt myself to answer a lot of questions on Slack about the latest problem set. So, oops, that's totally fine. What we are going to do is go over the project that I've been doing today. So this is round 2 of talking over the project. So the project for this week is singing piano. I did some prep work for this last time. That was last week. And the idea is that we are trying to create a music synthesizer that uses a piano as the source input into generating some music. And last week I went over a quick synthesizer crash course, which was what is a sound? A sound's a wave. What are overtones? Overtones are different modes of vibration for a wave. What are synths? They are basically ways to artificially create a certain musical sound, and the way you do that is you copy the overtone pattern, because two different instruments can play the same note, have the same fundamental frequency, but the amount of overtones and the types of overtones each instrument has will differ. So that's the idea behind a synthesizer. We're just trying to copy that overtone pattern and replicate it. So that was that. I talked a little bit about Mr. Joseph Fourier here. He's the fellow who invented the Fourier transform, which basically allows us to turn waves into a series of sine and cosine waves that combine together. And I gave a little bit of intuition for why this is the case, which I did not talk about last week. The basic idea is a wave is something where the more you push it away from its equilibrium point, so the more you displace it, the more acceleration you get, the more movement you get. Not just movement, but change in movement. And in math terms, acceleration is the second derivative of where you are. So what that means is that you have a function in terms of like second derivatives of things, and there's a very important thing which has its second derivative as itself. Those functions are sine and cosine. Those are the two functions where when you take the derivative twice, you get the same function back. If you're curious about why, you want to look into Taylor series, because basically they have Taylor series that are like every other derivative, every other polynomial power. So when you take the derivative twice, you get back to the same thing. And you can think of like the sines as like is odd. Yeah, sines are odd and cosines are even. So like they just take every other Taylor coefficient. So when you do a derivation, you're basically just shuffling, moving every single power down by 1. Right, so you get odd to even, and then even back to odd. Yeah, so that's kind of a really rough idea of why sine and cosine waves matter for these kinds of problems. But I guess the important thing that Mr. Fourier figured out is that you can actually take these sine and cosine waves, for which the solutions to these problems are easier to express, and you can actually turn those into any function you care about, which is like this random squiggle here. Right, so that's the special thing that the Fourier transform allows, is you can kind of move between this squiggle and a whole bunch of sine and cosine waves. So I gave a little demonstration of what that might look like. And then I talked a little bit about this whole idea of a discrete transform, which is where you chop up your signal into lots of little windows and you apply that Fourier transform to each one. And so the idea there is you want to be able to tell what your signal, in this case sound, is doing at different points in time, and turn that into a spectrogram, which is just a plot of frequency versus time. So today, what we're trying to do is create a synthesizer. So that's something that tries to copy this spectrogram, except we're not doing it with a computer. we're generating this spectrogram using a acoustic instrument, a piano, right? So we want to play a piano in a way that the output of that piano looks just like some other spectrogram that we specify. Okay, so that's the idea with the talking piano. And here's the thing. There is an algorithm to do this. There's a YouTube video where somebody does this, a pretty well-known YouTuber, in fact, Mark Rober. There's other people who have done this, but I would say their algorithms have some issues, which don't make them too good for composing music. So here's the issues. First one. We need constraints. So if you want something that's playable by a human, you can't just throw lots of notes at the problem. Right? So let's say I have a frequency spectrogram which has like 20 overtones, right? What I don't want is a output which has 20 notes, because humans only have 10 fingers, right? So you can only play 10 notes at a time, and they can't be too far apart, right? You can't have like one note down here and another note like way over there, because your hand only stretches so far. I'm like trying to move my hand, but then I realize the view I have is mirrored, right? So anyway, so the idea is your hands can only reach like an octave on average. So that means that whatever notes you have, they need to fit within like an octave and another octave, one for your left hand, one for your right. Right. And of course, you can't have more than 5 notes in each of those groups. So that's a constraint. You need something that's humanly playable. The other thing humans can't do is like play notes super precisely, right? So you can't like jump around too much or replay notes too fast. So those are the constraints on playability. Next is accuracy. So the way these current algorithms work is they just kind of throw a note at every overtone that they spot. So what they do is, if we go back to this picture, right, they look at every peak of this frequency graph, which I've sliced here, right? So you can imagine if I took this slice and laid it out horizontally, the peaks are where the frequencies are strongest. And at each of those peaks, basically, these algorithms throw a note on the piano at it. But the problem is that the piano itself has overtones. So the piano itself has some squigglies. And when you throw a note on the piano at this bump here, you end up with these extra squigglies later down the line in the piano's overtones. And so those are extraneous, and maybe they'll mess up the quality of the sound you produce in the end. So that's why I say in order to improve the accuracy of this synthesis, we need to take into account the source instrument's own overtones, which in this case is the piano's overtones. Right? Last one, envelope. So I gave a really long explanation of this. Let's do it again. So the idea here is that sound is not a fixed thing. It changes in time. And so when we talk about, to imitate this instrument, all you have to do is copy the spectrogram. It's not quite right, because it turns out it's not just getting this vertical slice correct. It's also getting the changes horizontally correct, because turns out the way we listen to sound depends a lot on the attack of the sound, which is the initial bit of the sound, which doesn't last very long. For example, when we talk, we need consonants, right? So saying k is a very short sound, but it really changes the kind of word you're saying. If I say ah, right, as a vowel, and I say ka, right, that's a very different sound to sa, right? Even though the ah part takes up most of the time, it's actually the little consonant at the beginning that matters a lot for which word I'm saying, right? Because save is very different than cave. Let's just put it that way, right? So the problem is that the attack is in musical instruments as well is often very different sounding than the sustain part. So for example, on a percussive instrument like a drum, when you strike the drum, right, that initial hit is going to impart lots of energy into the drum head, and some of those energies will vibrate at some weird frequencies and make these kind of extra vibrations, but those aren't stable because they're not part of the drum's kind of natural resonance. So after a very short time, those extra frequencies will die down. But what you hear is that kind of initial hit of the drum being different. It's like more percussive, right? Because you're actually getting a different frequency profile when you first strike it. Similarly, if I play the clarinet, which I used to do, if you tongue a note really hard, you articulate it, what that does is it kind of introduces these transient frequencies into the reed, and then eventually the reed settles into a steady state. That's your actual sustained note, but that attack is kind of what gives you a certain articulation to the note. So like, for example, if you tongue really aggressively, like ta ta ta, it's gonna sound more aggressive, whereas if you don't tongue at all, it's gonna sound very like mellow and smooth, right? So that kind of stuff matters a lot in music and musical performance, because it's actually the attack and the decay of the notes which kind of tells you what instrument you're playing and what kind of emotions or effect that you're trying to get across with the music. So this is a long-winded way of saying we need to consider the time dimension when you're synthesizing music. It's not enough to just match up the overtones, right? So now with these three problems in mind, we're going to try kind of rolling our own code and figuring out how to turn this kind of basic algorithm that we have previously into a more sophisticated one. Okay, so housekeeping, I was working on this earlier while I was forgetting to go live. So I moved the code that I have, that I lifted from GitHub, to a notebook so I can kind of mess around with it live. I have some sound from a piano, which isn't a real piano, it's just the program I have on my computer. So now we're on the transpose part. We have a loss function, which is basically a way to characterize how much difference do I have between the spectrogram that I synthesized versus the target spectrogram, right? So let's see. Yeah, so I think we're on transpose right now. So the idea is I need a way to kind of move around this source spectrogram so that I can kind of artificially cobble together the sound that I'm trying to synthesize. And then once I have this kind of fake spectrogram, I can compare it with the real spectrogram and see where I'm too loud or too soft, basically. Right? That's the visualizing differences part. Right, and then after that, eventually we might get around to this. And of course, there's also the issue of algorithms. So currently, I'm calling the one I downloaded a brute force algorithm, because it's just going through every peak and assigning a note to it. So I think we can immediately do better with a greedy algorithm. The idea here is that you're going to take, pick some fundamental overtone, assign a note to it on the piano, and then you're just going to update how much you've added onto the other overtones, right? So like, for example, you start with the fundamental frequency, you make the piano play that note, and then you notice, oh, that also adds a first overtone. And so you can subtract that from the first overtone. You no longer need to add that amount of volume to that first overtone. So you might be able to play the first overtone of your target sound a little softer, because you've already taken care of some of it on the piano. So that's the greedy algorithm. It's just trying to assign notes one at a time in the most optimal way possible. Okay, the annealing one, so these two are kind of more like learning or like optimization algorithms. So annealing is where you're kind of just moving around randomly, but in a controlled way. So you randomly just put a piano note somewhere, and then you shake it around, and when you find a good solution, the loss goes down, so it kind of sits into that loss. And now you try to find random solutions that are near that good point. And you keep doing this while decreasing the amount of randomness in the system. That's called the temperature. And eventually when the temperature goes to 0, hopefully you have settled in a low loss place. Right, and the reason why it's called annealing is because you can physically do this with metals. You heat them up, and then as they cool, the atoms inside are jiggling around, and they kind of jiggle into nice crystalline structures. And then as the temperature cools, they can jiggle less, so they kind of end up staying fixed in these nice crystalline structures where the energy is lower in the system. The last one I'm thinking of is maybe trying gradient descent to optimize this. So that's what machine learning people do. They try to optimize everything with gradients. So we could do that as well, I guess. The tricky part is that all of these algorithms will need to be constrained somehow, which basically means we need to limit how many notes are being played and where. Right, so remember that we're trying to make it humanly playable. So some of the problems that you face are like, not only do you have to make sure you don't play too many notes at once, you also have to make sure that the way you play them makes sense. So what I'm thinking is, like, for example, for the attack, we might allow more notes and then just release some of the notes after the attack for the sustain, and then finally for the decay we need some other release profile for the notes. What you don't really want is to like attack some more notes in the middle. I don't think that makes too much sense. So that's the algorithm problem. That's where I've gotten to so far. So let's jump into the code and see what's going on. Okay, this is actually good. I'm kind of, in hindsight, I'm glad I didn't start the stream earlier because it was quite disjointed with all the people asking questions. Which is still happening apparently. Let's see what's going on here. Oh, someone's asking something. Yep. Okay. So before I start talking about the code, let me just answer this question real quick. And I'll just close up everything so it... Yep. Okay, 1 second. Okay, so after that quick Q&A, let's jump back into this. So I've just copied out all the code from the existing code base that someone else wrote into this notebook, just so that I can kind of plot things live and not have to mess around with files opening and closing. So this is all just exactly copied from this file over here, process audio. So this one, I've just moved all of that functionality into here. So I'm just gonna close that up. So that's collapsed. And now what I've done here is I have plotted some spectrograms. So you can take a look here. If I plot these spectrograms, you can see here's one note, here's a different note. These are both piano notes, but one's higher than the other. And you can tell because this spectrogram, you can see the first fundamental frequency here is at 128 hertz, right? If we look at the next one, it's at 512. So that is what, four times higher. And the way music works is every time you double the frequency, you go up 1 octave. So this is 2 octaves higher. And that's correct because I actually generated this using MuseScore. I just produced 2 Cs. One's a middle C and the other one's 2 octaves higher. And that's exactly what you see. Now, what else is interesting here? Well, you can see that there's a bunch of overtones. And there's a lot more overtones for this lower C than for the higher one. That's because the higher frequencies are getting kind of cut out. I believe that's part of the processing they do in this particular software. But also, at some point, these higher frequencies, they go past the range of human hearing, right? So they become less and less audible to humans anyway, right? So what that means in practice is that a high note on a piano or any instrument is not going to sound the same as a low note. Right, so if I go Right, if I actually plot one more, which is the lowest note that I generated, this is 2 octaves below, and you can see, whoa, there's a lot more stuff going on, right? This is the fundamental frequency at 32 hertz, and there are a lot of overtones. Now, that's also part of the construction of the piano. Those low notes tend to be on really thick strings, and those thick strings have a lot of extra harmonics that are not supposed to be there. Let's just put it that way. It's, you know, it's part of what makes a piano sound the way it does, right? Okay, so anyway, so that's kind of the picture of some notes. Now, the next thing I wanted to do was transpose these. So the idea behind this is that I want to be able to load up these piano sounds and move them around to approximate the playing I want to create on the piano. Like instead of playing C, maybe I want to play D, E, and F. So I transpose this spectrogram to D, E, and F, and just by sliding it, you can just shift up everything in this picture, up or down a bit. And then once you're there, you also want to basically combine those spectrograms together, so you have a kind of simulation of what the sound will be like when you play D, E, and F. D, E, F, 3 notes all at once, right? That simulation will then get compared to your target sound. So for example, if I have hello and crash cymbal here, these are 2 sound bites that I pulled, one from the internet, the other is me saying hello from last week. So here's a crash cymbal. You can see there's just kind of noise everywhere, right? That's because a crash cymbal kind of creates white noise. So almost everything is just a wash, right? Here is me saying hello world. You can see the overtones of my voice very clearly. They're shifting because I went hello. I moved up in pitch in the middle, right? So that's why h is lower and o is higher. Okay, so the idea is that you want to take this kind of thing and just kind of turn it into this kind of thing. Or sorry, you want to create your fake version, right? And then compare it with this and see how close you are. That's the idea. Okay, so that's that. Let's close up the outputs so they're not taking up space. Now we're working on the transpose part, and then we'll work on the part that combines multiple sounds together. Just checking for messages. We're good. Okay, so the idea here is I need to be able to specify how much to transpose a note by, and the tricky part about that is that it depends on how far apart the frequency bins are. Now if we go back to the where the frequencies are generated, sorry, not here, here. So what happens here is you run STFT, that's the librosa function, short time Fourier transform, right? And the thing is you need this NFFT argument, which is the, let's see, the number of samples horizontally. Okay, so that's not actually what I want. I want to know how many frequency bins there are. Frequency bins, where are those? I think it just gives you a certain number automatically, but that's a little concerning to me because I want, so a lot of these audio transformations for speech tend to cap your frequencies at like 10,000 hertz because speech doesn't go much past beyond that, but the problem is music does, and we want to go all the way to the range, like the maximum frequencies that humans can hear, which is roughly 20,000 hertz. To be honest, most people can't hear up to 20,000 hertz. Like as the older you get, like by the time you have my ears, you've probably lost a good amount of that high frequency sensitivity. But we're still going to use 20,000 hertz as kind of our target for how high we want to go. So the question is, can we get all the way up there? So if I take a look at the outputs again, it'll kind of tell you. So right now it's going to what, like about 10,000 hertz. Yeah, that looks like 10,000 hertz. So we would like 20,000 hertz, which is double that. So basically we're missing a slice at the top of this graph. Okay. So let's dig through the this function again, STFT. So you can get the FFT frequencies using some other function. NFFT is not the correct thing because that's just the amount of time that goes into each Fourier transform window. So let's take a look at FFT frequencies if it's anywhere. Okay, so you can tell what's going on here. Signal rate is by default 22,000 Hertz, and by the Nyquist sampling theorem, that means that the highest frequency you can model is half of this. So this is why by default it's treating the signal rate as this, because that works for speech and for a lot of machine learning things, because 40,000 some samples per second is a lot of samples, right? It's very costly for computation. So yeah, we do want that many, so I just need to figure out how to tell it to work in this space. So I suspect what's happening is when you load the file here, it's probably giving you a lower sample rate. So I'm just gonna check that. So I can do that here. And let's just see what it prints. So 44. Okay, so that's the sample rate we want. Why won't it give that to me here in STFT? Okay, I might need to read the docs for this. So it says the default value corresponds to a physical duration of this at a sample rate of 2250, which is the default sample rate in libRosa. So I need to change the default sample rate. Okay, how do I do that? libRosa get sample rate. That gives it for a given file, but that doesn't change the default. Okay. So maybe I'll search elsewhere. libRosa default sample rate. Okay, so this is telling me there's a way to subsample your file to whatever you want. That's great, but that's not what I want. I want libRosa to work in the sample rate that I give. Okay, let's see what's going on here. So if you have a really short window, I know it affects how low you can go frequency wise, because you know, the bigger your wave, right, the more time it takes up. So the lower the frequency, the longer your wavelength, the more time it's going to take up. So, you know, at some point you can't detect that frequency anymore because it's too big for your window. But that should not affect the high frequencies. So that's why I'm confused by what happens to these high frequency sounds. And like I said, for speech, it's not that important because not a lot of speech sounds happen above these, above 10,000 hertz. But for music, it does matter because there's a lot of timbre that happens at those high frequencies. Okay, this is quite annoying, but you know what? For now, I'm just gonna leave it, and we'll just kind of note that there is an issue with the sample rate thing in libRosa. We'll just forget about it for now. So I guess back to the transposing part. What we do need to care about is basically how far you're transposing things up and down. So each spectrogram has a certain shape, right? So if I print here, oops. So what I'm doing is I'm loading a spectrogram, and it says that the shape of this thing is 2049 by 337. And one of these is going to be the number of, oh, I just realized something. Nope, that's fine. Okay, so one of these is like the number of frequency bins, and the other is the amount of time in it. So if I just load something else here, for example, like hello.wave. Oh, hello cat. Hello cat.wave. You can probably hear my cat screaming in the background for food, but I think you can see that, yeah, so this number changed, right? Yeah, so 371, 337, this number tells you how long this thing is, right? So basically how long the sample is, whereas this is not changing. So this must be the frequency bins. So we want the frequency bins, and basically we're going to transpose by some number of frequency bins, which depends on the amount of change we want in the sound. So we need some way to turn the number of bins into an actual frequency amount, or you know, just multiplying things. Like if we want to double the frequency, how many bins is that, right? So it depends on how these bins stack up, and I believe librosa has a function that lets you find that out. So let's do that. First of all, let's send in a scale amount. So the scale amount will be like a multiplicative amount that we want to change the frequency by. Let's call it multiple, okay? And what we want to do is check librosa. Librosa should have some kind of frequency to bins converter. And I just saw this function here, convert FFT underscore frequencies. That's the one. So let's look that up. Okay, so it says you have the signal rate. Oh, you know, I wonder if what's happening here is that I do have the correct frequencies. It's just giving me the wrong frequencies. Like, as in, I have the correct transformation up to 44K sample rate, but because this default is 2250, it's just plotting it wrong. That could be the case. Let's take a look. Oops, wrong file. Okay, so when I generated these guys, what you notice is, what I wanted to look at is how far apart each of these overtones is. So this is 1 octave. This is a 5th. This is a 4th. Yeah, those look correct. So maybe they are the correct frequencies. Okay, something to keep in mind. Okay, let's stop getting distracted and get back to this transpose function. So we need to ask librosa for the frequencies that we get from this bin. Oh, we might. So I just realized this number is affecting this. Okay, let's see. It's FFT window size. Oh, right. I need audio. Spec. Wait, no, I don't need that. Okay, I only need the signal rate and an FFT, which is 4096 currently. So if I do this, I wonder if the number will be different. I'm just gonna try it both ways. 22050, that's the default, and then do it that way. And let's just print both. Okay. Oh, of course I have to run it. So let's run it. Doesn't matter right now, we're not actually transposing, right? Okay, so we've gotten two outputs here. Interesting. Okay, so the first one goes up to 22,000 hertz. The second one goes up to 10,000 hertz, and that's because of these signal rates. Right? Okay, so I wonder if this is getting called in the code earlier. Yes, it is. But only in plot db, huh? How about plot spec? So I'm gonna go here. This is in the existing code that I downloaded. And what we care about is not these. Spec show. This guy, spec show, has a signal rate, you see? So that is a thing that we might need to change. In general, let's set the signal rate as its own thing, because I feel like we might need to change this at some points. So I'm going to create a new hard-coded value at the top, which will be signal rate. And maybe I'll turn this into an argument later, but for now I'm just going to do that, and anywhere I see 4800 I'm going to replace it. 48,000 I mean. So there's two places.
Signal underscore.
Oops. Yeah, I don't know why Windows is trying to print it out or say it. By default, replace all should be a Control-Alt-Enter in VS Code, but anyway, I can probably change that actually. Keyboard shortcuts. Replace all. Yeah, it's Control-Alt-Enter, so something's overriding that. Okay, that's annoying. Let me make a note to change that. Fix Control-Alt-Enter causes Windows to say things. That's kind of annoying. Okay, so where was I? Signal rate. I'm just replacing this everywhere, and that means I also want to replace it in spec show, which has a signal rate argument. So let's replace it. Okay. So if I just like rerun this and plot these, let's see what happens. Yeah, so now you can see it goes all the way up to 20,000 hertz. This is a log scale, remember, so like going from here to here is going from 16 to 20,000. Okay, that looks great. Is this correct? That's the important thing, isn't it? Yes, yes, okay, success. So we fixed the problem where we weren't getting all the frequencies. I think this is good now. Yeah, there isn't that much frequency information up there anyway, but at least we've got it reasonably correct. And I think what happened earlier was this was at 32 hertz, and I'm pretty sure middle C is like, sorry, lower C is more than 32 hertz. In fact, I'm gonna check this right now. Middle C frequency in hertz is about 260, yes. So yes, this is much better, right? Because you can see that's about 260 right there. Okay, so the fix was easy. It was just plotting the wrong numbers. That's good. Okay, let's hide that. Okay, so we're back to the transpose thing. I feel like I keep coming back and we just never leave. The idea is we need to run this again. And you know what? Let's hard code NFFT as well. This is the number of bins, just so I can refer to it constantly, right? So we'll say NFFT, and that's currently 4096. It has to be a multiple of 2 because it's faster to run that way. So anywhere we have 4096, we're going to replace with this. Replace all. Cool. Okay, so now we should be able to just generate one of these. Oh, of course, I forgot to run it. So yeah, that's one of the annoying things about notebooks. I don't always use notebooks because they can be a little annoying. Oh, I forgot. Yeah, you don't want to replace it everywhere because at some point you need to define an FFT. Okay. Okay, let's try that. And okay, now this is all of the possible frequencies that each bin corresponds to. So that is what we need in order to transpose things to the correct place, right? Okay, so step one, right? Step two is we need to turn this these frequency bins into some kind of multiple amount. So let's see. I have a hunch. So each frequency bin should, because this is in log space, each frequency bin should be like some fixed multiple of the previous one, except the first one, which is at 0, right? Yeah, that one does not make too much sense, but the other ones should be nice even multiples. So let's just test that. If I take everything after the first number and I just divide by the next one after that. So 2 divided by this, 2 minus 1. And let's do this. So I can get away with dividing an array because this is NumPy and they've kind of automatically defined division and multiplication and all these other useful mathematical operations over arrays. So this is doing some fancy stuff in the background, but here is what I care about, which is how much each frequency bin changes in frequency, and it's not fixed, so that's a problem. In fact, I'll just print the first 10. Or plot them. I can do that. Yeah, so that's a problem. So you can see the first multiple is like twice as much, but then the subsequent ones are not. So these bins are not evenly spaced as far as frequencies go, and that's a problem. That means I cannot transform things just by shifting everything kind of naively. Okay, let's think about what to do here. So the problem, if I try to draw it out, is we've got like a bunch of bins of frequency like this. Right. So each bin corresponds to some frequency of sound, and maybe some of them are louder like this. And what we want is to kind of change the frequency. So let's say this is like 200 hertz. Right. Well, and let's say I want to make this like 400 hertz over here. Right? Now, if these bins were just arranged nice and neatly by frequency, then what I could do is I could just take this and shift it up one bit like this. And so what I would end up with, is something like this. Right? So basically what I did was, because this bin is exactly twice this one, I just have to move it up, right? And if this was true for all the bins where the next one's like 800 and so forth, then it would be really easy. But that's not the case here, right? Because if this was the case, then dividing this number by this would give you 2, dividing this by this would give you 2, and so forth. Everything would be a multiple of 2 away. That is not the case here. Right, so let's move back to here. You can tell because of this, right? I just did that division between each successive frequency bin and the previous one, and you can see it changes quite a lot over the course of all these bins. So instead of just shifting everything, we actually need some way of kind of shifting some frequencies more than others. So let's see. you can think of each bin as having a certain amount of energy in it, and we want to distribute that energy up to some higher bin. So there's a couple ways to do this. The simplest way is to find the nearest bin that has the energy we want and kind of dump this energy in there, right? So actually, I'm just gonna take a look. I'm very curious about this FFT frequencies function, because what I want to know is whether this fellow is actually giving you the floor of the bin, or the middle of the bin, or the top of the bin of frequencies. So let's see, here's the code. It returns this guy, np numpy, right? Yeah, that looks like numpy. So I did not know numpy has its own fast Fourier transform, but it makes sense. So let's look it up in the numpy docs. Here it is. Okay. Okay. So it says frequency bin centers. Excuse me. Apparently I'm allergic to numpy. That's not good, considering I use it all the time. Okay, so we have window length, blah blah blah. Reading the docs. That's what this stream is devolving into, just me reading documentation. Okay, so we have It's interesting that 0 starts, because it's saying these are frequency bin centers, but if 0 is the center of a bin, you don't have negative frequencies, right? So that's a little weird. Spacing unit is in terms of cycles per second. So basically the frequency unit is in terms of the bins. But I think librosa does something different. Because yeah, they include this this guy, so yeah, they divide by the signal rate. So they actually give you the hertz instead of this. Okay. So if they are the middle of each bin, we'll just roll with it, and we'll just kind of try to find the closest bin and kind of throw our energy into that bin. That's gonna be the plan. So it's not gonna be perfect. This is going to have some issues with aliasing. Basically what that means is, like, if you have two bins that are kind of close, they might end up going both to the same bin when you do this transpose action, and so things won't quite line up. The proper way to do this is through some kind of like more sophisticated sampling method, but we will just do the dumb way first because it's faster and simpler. So basically I'm going to iterate through every frequency bin, multiply the frequency by whatever frequency that bin is, and that will give me where I want the new frequency to be, and I'm just gonna find the bin that does this, and that's the closest to this, and stick it into that bin. So for freak F in freak bins, and so I'm gonna go through the source first. So actually I need to go through spec, right? Let's actually do this for every single thing in spec. So spec has two dimensions. One is frequency, and the first one's frequency, right? The second one's time. So we want to go through the time dimension. So we want to go through all of this. Time slice and spec.t. So I'm just transposing this so that the first dimension becomes time instead of frequency. Once you have that, you're iterating over this number, which is the time slices, and then each of these will give you an array of the frequency slices. So for f in time slice, we're going to assume that we're doing it from like bottom to top. So the first bin is the lowest frequency, I believe. And so we might actually want to combine that. We'll say energy F. Actually, you know what? We don't need to do it this way. You don't need to use an iteration because, or a for loop, because NumPy allows you to do things kind of all at once. So we can take this frequency bin thing, multiply it by the multiple, which is the transposition we want, right? So let's say multiple is 2. Then we've transposed all the bins by 2, and we just need to find the nearest bin based on that. So oops, transpose bins equals this. Okay, so basically for each of the energy amounts in each bin in time slice, we want to map it to the closest bin in transpose bins. So let's see. This gives us our target, and we just need to find the bins in here that are the closest to that. So in fact, we don't need to do this for every time slice. We can pre-calculate it first. Sorry about the mess. This is getting quite messy, so I'm just gonna comment those out for now. So what do we do? Let me think. What I want to do is search through. So first of all, for each bin, we've got where we want the frequency to go, right? Then search for each bin, find the closest. For each transpose bin, find the closest bin, index. Find the index closest available bin. Yeah, we'll say it this way, right? So we have the target frequencies here. Now we need to find the bins in freq bins, which are closest to these transposed frequencies. So the way you do that is, I believe we can use NumPy search. So what it's gonna do is you run a search algorithm, basically. This array is already sorted, so it should be very fast, and it will search sorted. Yep. So NumPy search sorted, you can see let's see, it finds where an element should be inserted in order to maintain the order. Great. So that's what we're gonna do. We want, let's see, we want NumPy.search sorted, and A is going to be the sorted array, so that's your freq bins. V is the thing that you're trying to insert, so that's transpose freaks. Okay, and I think that's it, because the side is not going to matter. Yeah, because I can deal with the side, so we'll call this a bin index. Okay. So we can kind of run this on a very simple thing. Let me think. Search sorted. So you've got numbers like from, let's say, 0, 10, 20, right? So here's your bins, and you're going to search this array using NumPy search sorted. It's going to it's going to give you the index where something should be inserted. Let's say I have 15, right? So this thing 15 is going to be inserted between 10 and 20. So the side is by default left, which means it's going to, so if we look on the documentation here, it says when the side is left, it's going to give you the index where if you insert your value, it's going to sit. So basically, it's only an issue if it's equal to something, right? So actually, the side doesn't matter at all because we don't really expect these frequencies to be exactly equal. They're generally going to fall in between the bins, and if they are equal, it doesn't really matter which side we pick for the bin. So we can ignore the side, and what this will do is we'll insert 15 here in our example, which means that the index of this value 15 would be 0, 1, 2. It should be 2. And so if we remove it again, the index of 2 means 0, 1, 2. It means this is the closest bin according to our method. Now that's also not quite right because I realized that these are the centers of the bins and we want the thing that's closest to the center. So maybe a smarter and simpler way to do this, at least from a programming standpoint, is we're just going to calculate the difference between these transposed frequencies and these frequency bins, and we'll take the smallest difference, which is like dumb way to do it. It is computationally costly, but that's fine. The computer does the work, not us humans trying to think through things. So I'm just gonna do like oh, someone else is asking a question. Hi Ayush, did you just send me another message? Oh, I must have missed that. Okay, I'm gonna answer that question. Just give me a minute here. Okay, finish that. So jumping back into things, I just gave out the answer in case if you're still listening. You can check Slack now. Otherwise, I will go back to my project here. So what was the plan here? I'm trying to find the closest frequency bin to throw a sound into. So I'm going to do that using a very kind of cheeky way. I'm just going to take the difference between each frequency and all of the bins and find the smallest one there, which is very computationally expensive, but the good news is that the computer is doing all the work. So let's do that. First of all, I need to make this bigger dimension. So basically, I'm going to repeat this array over the dimensions of this so that I can get a number. Basically, I'm going to copy this array like freak bins number of times so that I can get that many answers. If I just do transpose freak minus freak bins directly, because these are the same shape, NumPy will assume that I'm just trying to subtract them one element at a time. So I'll just pair off all the elements, do the subtraction, and let's say this is size 1024 or 2048. You'll end up with 2048 different differences. But that's not what I want. I actually want 2048 differences per number in here. So I'm just gonna need NumPy repeat, I think. I always forget because there's two NumPy repeat functions. One of them is called NumPy tile, and one is called NumPy repeats, and they do different things. So you can see NumPy repeat does this. Let's see. Yeah, so it kind of interleaves the results, and that's not what I want. So I think I want NumPy tile. So you can see NumPy tile takes some array, and it kind of copies it out in its whole form. Actually, you know what? I don't think it matters here because in this case, I want to repeat things into a new dimension. So I'm gonna make this a two-dimensional array so that the subtraction only happens over one dimension. Actually, there's an even better way to do this, which is you can use NumPy's automatic broadcasting. So what I'm going to do is I'm just going to reshape this to be n bins and bins, where n bins is going to be equal to the length of freak bins. Oh, hello, kitty. Are you here to help? I think she's here to help. So yeah, so we're just going to reshape this. And what this does is when these two arrays are different shapes, NumPy will try to kind of match them up automatically. So this one is currently 2 dimensions, this one's 1 dimension, so NumPy will be like, okay, well, since I'm missing a dimension here, I will just add an extra dimension and kind of run it as if this number was the same over that entire dimension. So it'll just kind of copy it out for you. So if we do this, we also need the absolute value. And then we need to find the minimum, or this whole thing. So maybe it's better if I kind of split it up a bit just for clarity. We'll call this diff. And then we're going to take the NumPy min, and we need to specify which axis we're doing this over, because this is 2-dimensional. So originally this is 2-dimensional. Yeah, this is 2-dimensional. That forces this part to be 2-dimensional. In fact, I'll just switch the order so it's a little cleaner. So this is 2-dimensional. This becomes 2-dimensional as a result. And then we're going to take the absolute value everywhere. It's still 2-dimensional. And then we want to take the minimum, but only over one of the dimensions. So let's think. The extra dimension is going to be added to the front. Right? So basically, if you think of the bins as like 1, 2, 3, like this. Sorry, I have an example here, right? It's going to look like this. And so when it adds an extra dimension, now it's going to be the rows are all the same, right? Because the first dimension's the rows. And then the columns will be different. So it'll end up looking like this, right? Where you copy this out like 3 times, like this, right? So that's the array you get after you run, after NumPy does the broadcasting between these two shapes. And then it'll take that, subtract it with this, and then what we want is the minimum over all the subtractions per row, right? So that means that we want to do the minimum over axis 0, I think. we're gonna find out very soon if I made a gross error here. Okay, so min diff is going to be back to the original dimensions, which is just n bins. And so that tells us this minimum diff is going to tell us where we need to, where we have the best amount of, the least amount of difference with our frequency bins. So the only problem is we don't want the minimum, we actually just want where the minimum is. So instead of minimum, we want the argmin. So we can call this target ID, index. So the argmin just gives us where the minimum is instead of the minimum value, right? So that allows us to then take these indices. So this is where our frequencies should go. So we start with these frequency bins in the spectrogram, right? And so our source is, let's say, bins 0, 1, 2, like this. And then let's say we want to transpose everything by double. Let's say these are our bins here, right? So I'll just erase these again. Our target is, we still have the same bins, but now we want to move all of the energies in this bin into the one that's double that, right? So in this case, that means everything that's in this bin needs to go to the 20 bin. So that's what the target index does here, right? It's telling us that the index for this bin should be 2, so that when you do the transformation, you count 1, 0, 1, 2, you go to this bin, and you put the energy from this bin into that. So once we have that index, now we can go through all the time slices. For each time slice, we want to let's see. For each time slice, we want to. Man, it's been a long day. I had a pretty tricky presentation today about generative models. So yeah, I'm a little worn out from preparing and presenting that. I mean, it doesn't help when you're presenting a paper to the authors of the paper, 2 of the authors of the paper in the same room, and they're also the people who run the course, so they're grading you on the paper you're presenting, which they know all about because they wrote it. So yeah, that's not stressful whatsoever, as the kids say. Anyway, so back to this. For each time slice, we are going to okay, so for each time slice, we basically want to do this mapping, right? So whatever the value is in time slice, it's going to give you the amount of noise or decibels happening in each of these bins, and we just need to shift them over, right? So the trick is if any of these indices are like too high or too low, that's going to be a problem, right? So there's also a question of if this difference is too large, we actually don't want to move it to some index. So you can kind of imagine if we have this frequency spectrogram here, right? Let's say we want to transpose these noises up, right? The problem is that let's say it ends up way out here. On top of this graph, that's out of bounds, right? We actually don't have bins for frequencies that high. So we don't want to just have them pile up at this extreme frequency here. That would not sound good. And similarly, if we're trying to push this lower, right? We don't want those low frequencies to pile up here. We just want them to gracefully disappear. So we might need to implement something extra here, which is if the difference is too large, we're just going to mask out those bins. So those bins do not contribute to the transposed sound. Let's see how we do that. Okay, so if diff is too big, basically, we don't want to do anything. So we'll add a hyperparameter here, just a little hard-coded number, which is the maximum difference in frequency we're going to tolerate, which will be, let's say, something, what would be reasonable? Maybe like 50 hertz or something. Or you know what, let's use a multiplicative scale, because that's what a lot of this is based on, and we will use a diff threshold of 1.2 or something, 1.1. So what that means is if the difference is beyond 1.1 in the ratio, between the middle of this bin and the target frequency, we're just going to drop that sound. Let's go a little bit bigger, just because I don't know what's a reasonable threshold here. Okay. And incidentally, like 2 would be an octave, right? A multiple of 2 gives an octave. So multiple of 1.2 is like maybe a third, roughly, in music theory terms. So yeah, we'll go with that for now. That seems reasonable. So basically, if this diff is bigger than that, what we want is to kind of set those difference values to some default. So numpy.clamp, I think we'll do it. Clip. So clip is just a handy function for limiting how big your values can get. So we want to clip diff by a max. And I think I need to say a max, but yeah, that's right. So a max is going to be equal to this diff threshold. But the tricky part is these are absolute differences right now. So instead of that, I actually might want to divide. Yeah, so I want a ratio, right? Yeah, okay, that makes more sense. The only tricky part is that, of course, one of these frequency bins is 0. So we don't want to divide by 0. So I think we will need to get rid of the 0th frequency bin. There, problem solved. So now the frequency bins ignore the first one, which is 0. Right. And I'll just write a note. Remove first bin. Okay. Next, okay. We have our difference, which is a ratio now instead of just a subtraction. And actually, we don't need absolute because the ratio is always going to be. Wait, no, we need the closest ratio to 1. So we should just subtract 1, and then it'll be a number, you know, that's around 0, and absolute will make it strictly bigger than 0. Yeah, that's better. Because 1 means they're the same, right? If we divide 2 things. Okay, so we also need to clip the difference, and we're gonna clip this by yes. So we need like, so now we need a max and min clip because it can be either above or less than 1, right? Yeah, that makes sense. So obviously the lower threshold would be just the inverse, the multiplicative inverse of this threshold. Okay. I realize there might be some bias here because of so I just realized, you know, 1 over something is not the same as that same thing when you're trying to take the difference. So this is going to be biased towards one side of the bins over the other. In that case, I'm going to just turn everything into a ratio that's bigger than 1. That would be simpler. So that will allow us to remove numpy abs, and the way I'm going to do this trick is I'm just going to go through diff, and anything where it's less than 1, I'm going to take the inverse of. So actually the better way to do it is to take anything that's bigger than 1 and divide and take the inverse, because otherwise you might divide by 0, right? So we're going to do diff less than greater than 1. And we can index by this condition because numpy is magic. So basically take everything where the difference is greater than 1, and we're going to set it to same thing but 1 over that value. Okay. So this is just make sure all ratios are less than 1. Less than or equal to 1. Yeah, so that's great. Now we don't need to clip it in both directions. We only need a, you know what, I'm going to change this to be this way just because it's easier. So now we only need a max threshold because everything is, do we? No, actually we don't need to clip it anymore because it's going to go from 0 to 1. It won't exceed 1 because I've divided everything that's bigger than 1 this way. So it will always be like this, and the minimum, it could be negative. Could it be negative? No, it can't, right? Yeah. Yeah, because the biggest it can get is 1. It cannot get bigger than 1, and if it is 1, then you get 0 here, which is what we want. That's the smallest you can possibly have, so that's perfect. Now the diff could be huge though. Right, so I think this needs to be argmax, right? Because let's say the difference is like, no, the difference is ratio. So the ratio cannot be, it's going to go from 0 to infinity here, right? So, and now it's, once you do this, it's going to go from 0 to 1. So yeah, we're good. Okay. Of course, there is also the issue of, oh, right. The whole point of this threshold is to get rid of some of these differences. So basically, we need to generate 2 things, which is the min and best diff, we'll say, and then this is the target. So the idea is, actually I can do it slightly differently. I can just do this, diff target index. So I'm just pulling out the difference from this array. So I'm using this index to find it here. Can I do that? Yes, but it's a little complicated, so I'll just leave it this way. It's a little easier to understand. Okay, so the idea is if the best diff is greater or more extreme than the diff threshold, so in this case it would be less than because we're dealing with ratios where the numerator is smaller than the denominator. Yeah, okay, so when this diff exceeds this threshold, then what we want to do is take any of those differences and set them to some special value that we can reason out, basically. Or right, okay, I see what to do. These are going to be the values that are excluded. So what we want to do is target I can do this. So numpy.where gives me the indices where this thing is true, and then remove index equals this. So these will tell me where I should ignore the frequency, the energy information in the spectrogram, right? So basically, when I get this time slice, the first thing I'm going to do is I'm going to take all the places that are in these remove indices and just set the amount of energy in those to 0 or something like that. Yeah, actually, I don't know if 0 is the right number because a lot of these are, I'm not sure what format spectrogram is in, because if it's in like decibels, 0 is not the quietest you can get, right? But we'll just say to do here. Okay, and then for everything else, we're going to, so for each time slice, we're going to basically transpose to target bits. So first we get rid of the ones we don't want to transpose, right? And then the next thing to do, we might want to copy this first, actually. Okay. We remove the ones we don't want, and then we are going to move these to the target index. So we need a target array. Yes. Just call it output. and we'll just append something to output. Okay, so transpose is going to be our new array. It's going to be empty first, so it'll be numpy zeros, but zeros like time slice. And then for each bin in transpose, we're basically going to take time slice. So basically each thing in time slice needs to go to this target index. So the way you do this is you do like transposed. There's a problem, which is like some of these target indices could be the same. So in this case, I will use another for loop for index. And we take transpose at index, and we need to add the value at time slice. And time slice. So we need to iterate through both of these together. So time slice gives you the energy at a given bin, and then the target index tells you where to put that energy in the transpose version. Right? So zip those together. We have index as well as the energy. So that's it. And the reason why I'm doing it this way with another loop is because this index could overlap, right? You could end up with two different source bins that get mapped to the same target bin. So that way I can add them up together. And hopefully adding is the correct thing to do because there's like different ways to measure this energy. Like for example, if it's amplitude, if it's decibels, adding is the wrong way to do this because those decibels are already transformed to log space, right? So I'll say to do okay, so I'm not sure what the format is when I run transpose, so I'm just going to ignore that for now. Now I can stick this thing into output, and then finally concatenate output together. And stick everything together in axis 1, transpose it back so that it is frequencies and then time, right? And we can return the whole thing. Okay, that was a lot of work to make a very ugly function, but in theory, it should do the thing where we want to transpose something. So let's give it a shot. We have loaded a spectrogram. We plot it, let's plot it. And then transpose it. And we'll transpose by like 2, so that gives us 1 octave higher, and then plot the transpose version. Okay, so I'm almost certain this will crash and burn, but we should do it so that we know where the errors are. So it says, okay, so this is the first plot, and then it says there's an error transposing diff frequency bins. Okay, so I did not specify how this should work, that's why. Oh, no, I see what the problem is. It can't reshape to this, right? So, I think you can do that. X is out of bounds. Okay, so the issue is whatever this is wrong now. Okay, so what I fixed here was just I realized you can't reshape it with things you don't have. We only have n bins worth of stuff, so you can't change the shape of this array, but you can add a new dimension. And when you do that, the broadcasting will kind of try to match this last dimension. So because this has n bins, it will kind of repeat this guy here over n bins. And let me just double check that's actually happening, because maybe that's not, and that's why I'm getting other errors. So in theory, diff should have a shape of n bins times n bins. Let's see, yes, so that's correct. Okay, so after this though, we need to see what happens to transposed. Is this the correct shape? This guy here. transpose that shape, we expect that to be just n bins once. Yeah, and that's good. So when we get to here then, let's find out what's happening here. Oh, I see. Okay, elementary mistake. Concatenate can only combine arrays according to their existing dimensions, whereas stack lets you create a new dimension. We need to create a new dimension here. So let's just check the shape here to make sure it's the correct shape. It should be the same shape. Oh, I got it backwards. I got it backwards. Okay, it's because I already stacked it along axis 1, so that's the correct axis. Okay, let's try that again. That's good. Okay, and that's less good. So you can see this part's fine, this part is not, and I have a feeling something happened when we're adding things. Let's first take a look at this energy value and just kind of see what the value is. 0J. So these look like, yeah, they look like complex numbers. So that's probably why things aren't working. Although they're also weirdly all 0. That's very strange. Huh. That sure is kind of strange. So actually, let me see what the stats on time slice are. So I just want to see, like, what's the minimum, what's the max? Like, what numbers are we dealing with here? Okay, minimum 0. Maximum is pretty small, but it's non-zero. And then here's the mean. Okay, I understand. These are indeed complex numbers. Okay. So let's see what happens to, instead of this time slice, let's see what happens to the one that I add to transposed. Because if it's all 0, that's a problem. Yeah, so it's somehow, it's not going into this, this guy here. So let's just try overriding. It's still not happening. So somehow this energy is not going in. Interesting. Oh, right, because it's 0 all the time. Interesting. Really interesting. Why is that happening? Okay. That's actually odd. I haven't worked with NumPy and complex numbers before, so this is new. Okay, so that's fine. It might be, is time slice the correct dimensions? Let's check that. Yes, that's fine. Okay. This should be the same shape. I'm really curious, like, does energy ever... Does energy ever go to non-zero? The answer is no. So somehow when I'm iterating over this, I'm not getting any non-zero values. I wonder if it's because you can't use these kinds of comparisons with so complex numbers, you need to compare the magnitude. Yeah, so I wonder if, oh, nope, there's one non-zero here. Huh. Okay. Well, this is sure kind of mysterious, I gotta say. Huh. Okay, let's try something. Let's try just moving time slice over. Just kind of for a sanity check, you know, instead of doing this the proper way, I'm just gonna see if I can reconstruct the original. I cannot. Okay, so something weird is happening here when I slice up things by time slice. Maybe it's the copy? Oh, or maybe it's this. Maybe I bet it's the threshold causing issues. I forgot about that. Yeah, so it is indeed the threshold. This threshold is actually canceling everything. So let's try doing this again. Okay, this is promising. So I said I was trying to scale everything by a factor of 2. I think I actually scaled it the wrong direction, because here you can see 128 is now at 64. So I scaled everything down, and I actually want to scale everything up. So that should be easy enough to fix. In the multiple part, frequency bins multiplied by... Huh. Yeah, why is that happening? So if I multiply the bins by 2, right? That means I'm trying to go to double the frequency. I'm really surprised by that's going the wrong way. Okay, well, that's probably not too critical. What I do want to change is, let's change this to piano C4. Run it again. Let's try 0.5 this time, so that should cause it to transpose in the other direction. Yes, and it does. And you can also see the aliasing. It's pretty obvious here, right? Yep, that's a lot of aliasing. So the aliasing is all those dark bands. It's because like some of the bins are getting preferred over others. Okay, but at least it's kind of working. So that's good. So the next problem is why this removal is not working. So let's see. The move indexes are where the best difference is less than the threshold. So I'm gonna print some stats first. We're just gonna ask what's the min, max, and mean of this. Okay. Okay, so these ratios are quite small. Oh, it's because I subtracted 1, that's why. Okay, I see. So, what we want is like... Okay, I understand what happened. So I think I can just do this, right? Yeah, okay. So that's why. And let's see, what's the biggest difference you have here? 0.15. Sorry, 0.5, right. Okay, that seems reasonable. Oops, I forgot to add this in. So this is the removal bit. Oh, and it removed everything. Okay. Let's bring these stats back. Let's see what's going on here. Oh, it's because it's less than. Right, because I took 1 minus, so it should be greater than. Okay. Phew, disaster averted. Yes. Okay. Great. So I'm going to try something different here. I'm going to try transposing the really low note, which is C2. And I'm going to try transposing it down quite a bit so that we can see whether the really low frequencies get clipped out because the difference is too big. Because right now this is bugged, I need to put in a bigger number here to make it transpose down, even though it should be the other way around. Okay, so what we expect is that this extra nonsense at the bottom should go away. And it kind of does. Let's see. Let's go a little crazier. Let's transpose it down 2 octaves. Okay, so basically it should go, this part should go down to 16. Yeah, and it does, right? This is about 32, this is 16. Yeah. Okay, nice. Okay, so I think it works. Because I'm not seeing a whole lot of stuff down there. And in fact, let's just double check that. If I remove this part where it cancels out those things, or I could just set the diff threshold. Actually, that's the other way. So right now it's removing things where the difference is too big, but I could change that. I could change it to do the same thing, but we'll set the threshold to something like 0, I guess. Does that make sense? Because then it would be yeah, the best difference is bigger than 1, which should never happen. And so let's see what happens. So with threshold, without threshold, honestly, they look the same. I'm really surprised by that. Like, it should not... Oh, it's because I actually didn't comment it down. Okay, let's try that again. Okay. Any difference? I cannot tell at all. Huh. Let's print out how many indices I have as well. Okay, and I'm not getting any more messages for the course, so that's good. People must be finished. Okay, so omitted bins, I don't need to know exactly which bins, but let's just give the length, the number. Yeah, so it only omits 1 bin. That's interesting. Oh, it's because this threshold is pretty generous. If we increase the default threshold to like 0.9, I'm sure... Wait. Huh. Well, let's just keep bumping it up until something happens, right? No, both are... Huh. No, this was definitely not length 1. Something happened here. Yeah, so, okay, I see why. It's because where gives 2 arguments. I forgot about that. Because NumPy where gives you enough, like, basically, it needs to give you a separate array for each dimension. So we do not want that. Okay, that's better. That makes more sense. Okay, and if we compare them, yeah, you can see that some of these just got completely taken out because they're too different. Then basically these bins are too wide, and so now they're too different for this algorithm to match up. So it said, nope, you're not allowed to do that. So let's lower the threshold a bit, make it a little more reasonable again. Okay, so yeah, that seems to make sense to me. Okay, we're gonna set it the threshold back to 0.8 because that seemed reasonable, and let's see. Instead of printing the whole thing, we will print the length. Yeah. Okay, cool. Let's see what goes on. Yeah, that looks reasonable. Excellent. Okay, so that generally works. There's a lot of aliasing when you transpose up, but it seems reasonable when you transpose down, and the only other thing is this multiple thing. So, you know what? I'm just going to hack it. I'm not sure exactly what's going on, so I will just do that. And now it should transpose up as expected. So let's see if that's happening. 64 should go to 256. Yeah, and it looks like that's what's happening here, right? Yeah, so great. Kind of works. Now, of course, transposing by 2 octaves is going to not be accurate at all. So I think more realistically, you'll transpose things within an octave. So 1.5, for example, would be transposing by a 5th. And if we plot that transposition, it should look quite reasonable, even with the, actually it's not super reasonable with the with the aliasing, but it's like not bad. And what we could do as a hack to get around the aliasing issue is just always transpose down. So you never transpose like up. So for example, if we go down a 4th, I think this is down a 4th. Yeah, these look totally reasonable, right? Yeah, so before the fundamental was at 64 Hertz, now it's a little lower. Nice. Okay, although this threshold seems a little too aggressive, so I'll just increase it a little bit, make it more generous. Yeah, so now you don't get any black bands at the bottom. That seems totally reasonable. All right, so we've got our transposition thing. We've got, I'll just remove all the test code. This seems to be fine, so setting these to 0 is fine because it's not working in amplitude space. So now that we've got the transpose part, we've got, let's see. So let's go back to the kind of the to-do list. Close all this. Okay, so we have our source audio, we have our source instrument spectrogram, we have our loss function, we can transpose the source spectrogram around. Now we just need to be able to add them together. Okay. It's getting pretty late though, and that sounds like another big project, so I might just try transposing some notes and seeing how they sound using this function. So let's try that. Load spectrogram. Wave, we'll say piano C2. We'll go with the higher ones. We'll start with middle C. We'll also do maybe the high C, and then I will transpose each of these. C4 to, let's say, down a 4th, and I'll do the same thing for C2. Okay. We'll leave the threshold as is. So this should be C, well, this should be G3, something like that. And this should be G5. Okay, and so, oops, C6. Okay, so once we have these 2 notes, we just need to turn them into sound again. So right now they're sitting in a spectrogram format, and libRosa allows you to undo the STFT transform, the short time Fourier transform. I think it's called libRosa.invert STFT. Let's see if that's correct. Function ISTFT is the inverse of the short time. Yeah, that looks correct. Okay, so it's not going to sound super pretty because this inverse is not super accurate. I know this because I used a wave normalizing flow instead in that Leonard Cohen project to do this inverse. And incidentally, this is why a lot of audio stuff in machine learning will do end-to-end translation. So what that means is you don't change it into this frequency format at any point. You just work directly on waveforms. Although that's got its own problems because waveforms just take so much data, right? You're sampling at a rate of 44,000, or even with the reduced sample rate, 22,000 samples per second. You know, that really adds up over time. So anyway, STFT matrix, that would be our G3 and G5. And do we need anything else? Parameters, hop length, number of frames between. Okay, that should be fine. We didn't touch any of these. We do need to add NFFTN. Oops. We have our global number for that. We're using defaults for everything else, so I think the rest is fine. Okay, and so that will give us G3 audio, and similarly with G5. Okay, so basically what this inverse does is it takes our array, two-dimensional spectrogram array of frequencies and time, and each of those numbers in here is a complex number, so that's how you get both phases, the sine and the cosine waves, because the complex number has two components. And then you run the inverse on it, it just undoes the transformation for each of these windows, and then you should get basically a one-dimensional array of the audio. And then once you have that, we can write the audio somehow. librosa should have a function to do that. So let's do a little searching. Utilities, file operations. Nope. Core IO. Audio loading. That's loading. Okay, I will do a little Stack Overflowing. librosa save audio wave. Okay. Well, someone's complaining about some issues, but there is librosa output. So I found librosa.output. Right. Is this a valid function? I guess we will find out. Let's just try running it on its own. It says librosa does not have this output. Huh. Okay. Do I need to import it? Okay, so there is something called an audio IPython display. Okay, interesting. Okay, so instead we're gonna use the notebook to do this apparently. So a notebook, Python notebook is actually its own kind of like program that runs things in this interactive way. And so I think what this allows me to do is just run some audio directly in this notebook, which would be super helpful. So let's see, it creates a display object from this data. So if I run like G3 audio through this, let's see if that does anything. Hang on. So we need to specify the rate. Rate must be specified when data is a NumPy array, so we need, what is the argument for rate? URL, okay, rate, okay. Rate is going to be our sample rate. Autoplay, okay, cool. Sample rate is not defined. Really? Because I distinctly recall defining it at the beginning. Signal rate, oh, oops. Yeah, that is definitely the wrong terminology. So let's just rewrite this. Sample rate. Can't believe I called it signal rate. Okay. This is why naming is a thing. You know, in computer science, you think, what's the point of names? Like, it's not like the computer cares what things are called, and it's true, the computer doesn't, but the problem is humans are reading and editing these files, and so it's pretty obvious you need good names for things, otherwise people get confused, right? Okay, so now we actually have audio, and it's a question of what that sounds like. In fact, let's actually load the original, maybe, audio. Yeah, let's try this. Before we do the load spectrogram thing, we run this sf.read, and that gives us some data and a sample rate. So what you could also do is this. If I just do this, can I get the original sound? I don't know why it's only creating one of these though. Okay, that's fine. I will just separate it into its own cell. That's fine. Yeah, okay, so great. Now, I, in theory, have 3 audio files. One should be the original C4, middle C, and then the other 2 should be transposed versions of either mid C or the high C. So let's give those a try. First of all, the original C, and just to make sure the playback works. Okay, playback works, that's good. Now this is the transposed one, which was, let's see, G3 audio. So it should be the middle C transposed down a bit. Yeah, so it kind of works. There's some weird stuff happening. That's probably from the inaccuracies in moving the bins around. Yeah, so the things you hear are, it's like some of the overtones are out of tune. And that's why it kind of sounds like a bell, because bells tend to have out of tune overtones, and basically the way we're matching up these frequency bins isn't quite accurate enough, and that's why you get this kind of effect. Okay, this one is the higher C that's been transposed down. Okay, that one sounds pretty good actually. It's pretty accurate. If I play it again. Yeah, so again, you can hear there's a little bit of inharmonic stuff happening. In fact, let's just try playing the C6, which is the higher C, because I'm curious to hear if it has some of that in the attack anyway. No, it doesn't. But when you transpose it down here, yeah, it has some of it. So yeah, the transposing's not perfect, although we are still transposing by quite a bit. So what if I transpose by like a smaller interval? Let's try that. So this is mid C again. Oh, sorry, not mid C, that's high C. Okay, I transposed it by roughly a whole tone. Yeah, so it's still pretty off. Yeah, so we're gonna have to deal with that aliasing issue next time. I can't just hand wave it away, but let's try running this one. Yeah, definitely you can hear the aliasing, but that's okay. At least we have a proof of concept, right? I will turn this, so music back on, check for messages, we're good. So I will turn these into maybe its own function just for convenience. We will say maybe put this on top. I'll create its own little thing. Def playback, and I'll have a file, or you know what, just an array. So here I will just have to run this, I think. Yep. Okay, so now if I want, I can probably do something like this. You know what? I'm gonna make this a little more sophisticated, which is it'll just automatically detect if this array is in the correct format or not. So if length array.shape. So if the number of dimensions is greater than 1, we're going to do the inverse transform. And then generate the audio out. So that way, I believe I can just do this. Playback C4, G3, C6, and G5. And I just realized something. One of the reasons why you might be getting these inharmonicities, these bad sounds out of this playback is not necessarily because of the aliasing, but actually because of this inverse transform. That could also be messing things up. Okay, apparently it doesn't want to... okay, that kind of works. Although it doesn't want to do multiple ones. So I wonder if there's a way to do this in IPython. More than one audio object. Thank you, Stack Overflow. Display.display. That's what I'm missing. Okay. So in theory, I can do this. Yes, okay, great. So I have C4, G3, C6, G5. Now I've generated them all from the spectrograms. So in theory, we'll be able to tell whether these weird sounds we're getting are due to the STFT inverse or if they're actually due to my transposition. So let's give it a shot. So I don't hear anything weird going on there. So it seems like the inverse is doing just fine. It's not the inverse. Yeah, that one still has issues. Oh no, this one's different. Okay, so if I load the spectrogram directly, sorry, if I load the audio file directly, I think this gives data and sample rate, so I only want the data bit. Yeah, so you can hear the difference between that one and that one. Although they're also in the wrong octave, which is a little weird. Okay, so it sounds like actually I'm getting the wrong octave anyway when I do this spectrogram thing. Huh. Everything's getting pushed down an octave, which probably explains why things are not sounding the way they should. But if I just, like, for example, if I compare this with our C4. So the first one is loaded directly from the WAV file. The other one has gone through the Fourier transform and then the inverse. Yeah, and somehow going through that process has dropped it down an octave. So yeah, that's an issue. The question is that happening because of this or because of that? Huh. Okay, well I can plot the spec for C4. And remember, middle C is about 260 Hertz. So this is correct. This plot at least is correct. So it seems like the issue is in the inverse STFT here. It's probably getting the wrong sample rate or something. So I must be missing something. Let's see what happens when I run STFT. What am I running STFT with? Load spectrogram. Hop length. I'm missing hop length. Maybe that's the issue. So let's go back down here. Oops. Yeah, I'm just gonna rerun this to get rid of that extra window. Okay, so when I run here, I need a hop length. Let's see if that changes anything. Nope. So it's the same. Okay, so I'm not sure what's going on here, but I'm not gonna go any further today because I did get, we made some progress. hit a lot of roadblocks, and my brain's a little fried from coding so much. So there's not too much time left. I'm just waiting until the deadline of tonight's problem set goes through so that I can answer any last minute questions, although I think I've already done that. It seems like most people who needed help have already come and gone. So maybe this is a time to kind of relax a bit. Yeah. I'm trying to think, like, what would be kind of a fun side thing to do? You know, what I'm feeling like is, let's see. Well, I could browse some. So this is something I was thinking of doing for fun. I could look at some statistics memes. That's always fun. So there's a subreddit called Statistics Memes, and I'm just pulling it up offline. Off screen, so that I don't pull up anything incriminating by accident. But maybe I'll just look through a couple of them and rate the memes. So let's see. Number 1. Statistics memes is my favorite niche subreddit. It's got a lot of humor that probably is not funny to most people, but you know, that's what gets people off. So this is a Nova one. Me when I'm researching a model and stumble upon an even cooler model. No, one model at a time. I can totally understand this feeling. There's just so many models out there, and this is probably not even thinking about like machine learning models where there's just a dime a dozen, right? ANOVA is a model for variance in the classical statistics standpoint. So yeah, I mean, something we forget about, I think, in the machine learning world is there's a lot of traditional, like more classical statistics models out there that aren't flashy and exciting, but they're actually used by a lot of people, a lot of companies, because they're boring and predictable, right? That's kind of the selling point. So yeah, now that I've ruined the humor for that one, let's go to another one. Oh, I like this one. True story. My kidnapper returning me after listening to me talk about moment generating functions for 2 hours. So yeah, I think I would do the exact same thing if I listened to someone talk about moment generating functions for 2 hours. Actually, that's debatable because they are pretty cool, admittedly. So moment generating functions, if I recall from my stats career, or education, I should say. I haven't really had a career in it per se. So at least in intro stats courses, they're like, here's a moment generating function. You should memorize how to do this, and enough is said about that. And that's about as far as they get. But they're actually pretty cool. So the idea is you create a function where if you take the derivative repeatedly, it actually produces the moments you want. And I believe the context for this is that it's a transformation. It's like a kind of what's it called? Starts with an L. It's like a Taylor series, but more sophisticated. And the idea is that because of this relationship between like the moments, moments of a statistical distribution really are just like a kind of like, it's like a Taylor distribution for the statistical function, right? I always wish they would kind of teach at least some of the intuition behind that in these intro stats courses instead of just asking you to memorize them. But yeah, depends on how well this person's talking about the functions. Depending on that, I would either throw them through the window or listen to them very happily. Okay, next. Oh, this one's good. When a panelist claims that their non-significant p-value proves the null hypothesis. Yes, in that case, they are indeed falling victim to one of the classic blunders, and apparently even professors fall victim to this. It's just the way we talk in language about the null hypothesis and so forth is like really messed up and confused, and it's often taught in a confusing way too. So let's see if I can go through this. Andrew Gelman has a really great article about what p-values are and what they're not. So I forget what the article is called, but if you look up Andrew Gelman, he's one of the big name statisticians out there. But the idea is that when you're doing significance testing using this kind of whole p-value setup, the way it works is you're trying to detect an effect. And to detect an effect, you're basically rephrasing the question as, suppose there was no effect. How unlikely would we be to see this data given that we pretend there is no effect? In other words, how likely would it be that our result is due to random chance as opposed to some deliberate thing? So you can think of this as like, let's say you're trying to prove that someone's cheating at some kind of game, right? So you suppose that they're not cheating. You pretend the opposite's happening, that of what you're trying to prove, and you're basically asking how likely is it that if they're not cheating, they would get this result by pure chance. And basically you can calculate this out, and that will give you your p-value, which is the probability that this thing is happening by pure chance. And the thing that you're saying is under the null hypothesis, which is under the hypothesis that nothing's happening out of the ordinary, like they're not cheating. This is the probability, the p-value, that they could get this result, right? So the problem with this is we start by assuming the null hypothesis, right? That doesn't make it true. And it also doesn't make it false, right? We're just assuming it. It's like saying, like, I'm going to say, suppose the sun was green, and then I'm going to do some analysis based on that, right? It doesn't mean that what I just supposed is true or false, right? I just picked it from my behind, really. There's nothing forcing this statement to be true or false. So when you end up with a non-significant p-value, basically you've picked some kind of threshold for when you decide whether this thing is true or not, right? And so let's see. So you have to pick this threshold beforehand, because otherwise you could pick it to be whatever you want. And so if you have a really unlikely p-value, like it's very low, that means that under the random chance assumption, it's very unlikely you would get this result. So you say, okay, then we don't think it's due to chance because it's unlikely under random chance. Now there are problems with that, because the probability under of random chance based on an assumption you made is not does not imply the opposite. And if you talk to a Bayesian, if you think about it in terms of a Bayesian statistical framework, you can see why these things don't make sense. These arguments don't really make sense to begin with. But the flip side is you have a non-significant p-value. That means that assuming that this process is due to random chance, it's very likely that what you've observed is also due to random chance. So it's like you assume that this person's not cheating, you look at their play, and turns out the scores they're getting are pretty likely under the random. Just you know, if you play regularly, you would expect to see this pretty often. So then that tells us that if we assumed the null hypothesis, it's pretty likely you would see this outcome. But also that doesn't mean the null hypothesis is true. It could be some other hypothesis. Lots of things could be happening. In fact, that's the whole problem of statistics, is there could be a lot of models, an infinite number of models that explain your data. And the question is, which one do you pick when you don't know which model explains things? You know, I've had this explained to me like this. Probability is when you study something from the standpoint of knowing what the model is. And statistics is the opposite. You don't know what the model is, and you have to recover the model. And it's way harder to do statistics than probability, because, if you start by assuming a model, it's really easy to do the math and just figure it out from there. Yeah, so this is indeed a foolish thing to do, but also a very common thing to do, unfortunately. And maybe that speaks to the quality of stats education around the world. This is pretty classic. What's this one? Oops. It's loading. Okay. This is a classic meme format. Never take the mystery out of machine learning. We need someone to do high-tech machine learning like Lasso. And then this poor sucker here says Lasso is just optimized linear regression. And out the window you go, because well, he's right. So Lasso is what is it? It's like man, I can't believe I'm just explaining these jokes. This is like, frankly, like, must be the most boring thing ever. So Lasso is just like a way to do linear regression where you're going to get rid of some of the parameters. And the reason why you would do that is because linear regression can overfit, meaning like it's just giving you a result based on noise instead of actual data. And Lasso is the least absolute squared shrinkage operator, which is just a really fancy way of deciding which of the linear regression terms to get rid of. So basically you're making a decision on less data, but hopefully it's the data that actually matters for whatever decision you're making. I mean, yes, Lasso is just optimized linear regression, but actually it's used all the time because it's like pretty stable and like predictable, right? Unlike neural networks or something. So based on these memes, I guess I should rank them, huh? So I would say, if I go here, this is pretty good. I like this one. It's very understandable. It's like it's funny. So I would rank this one like 9 out of 10. Yeah, it's pretty good. It's not the best I've seen, but it's pretty good. This one, like, yeah, the problem is this is a stats audience, so I feel like, I don't know, maybe we identify more with, you know, the person who talks about moment generating functions for 2 hours. So I don't know. We'll take a few points off. This is how I grade the assignments, by the way. So 7 out of 10. That's an ad. And this is, yeah, I mean, like, I can understand this, but I also think it's like not too funny. It's hitting a little too close to home. It feels like, you know, some thought that goes through your brain pretty regularly. And it's like, yeah, I'm gonna say 6 out of 10 for this one. Yeah. Okay. And of course, this guy at the bottom, I would say, I mean, it's a pretty classic meme format, but like it's been kind of overused. So I'm going to call this like 6 out of 10 as well. Yeah. Okay, so that's the meme review for this week. And I think that will be it. I'm gonna call the stream, I think. Yeah, because there's 10 minutes before the deadline. I'm sure that anyone who wanted to ask questions has asked questions. I'm pretty tired from a full day. So yeah, that's it. Hopefully next week I can get a little further on this project of the singing piano. And we will end it right there.